Welcome to Systemic Stack. This is episode 3 of the System Engineering series, and today we will explore availability versus reliability in a way that helps you prepare for system engineering interviews on this topic. Well, it's easy to treat these as identical, but interviewers really look for that specific distinction between staying reachable and staying stable over time. We look at how metrics like MTBF and MTTR drive your design choices, so you can walk into your next interview ready to justify your architectural trade-offs with total precision. We'll begin by untangling the fundamental difference between availability and reliability. It's a classic interview pitfall to treat these as identical, so we're going to break down why uptime percentages don't tell the whole story. From there, we'll dive into the math, looking at metrics like MTBF and MTTR. You will see how these numbers actually dictate your system's nines and, well, how a fast recovery can sometimes mask a shaky architecture. Then we'll shift gears into the design side. We're going to examine redundancy and failover mechanisms, but we'll also tackle the messier side of things, like partial failures and those dreaded cascading outages where one small blip brings down the whole house. Finally, we'll weigh the actual costs of chasing perfection and compare how a high-stakes banking system approaches these trade-offs differently than a global social platform. By the end, you'll have a clear framework for deciding when to prioritize raw uptime and when to focus on bulletproof consistency. Now, let's get the definition straight, because your interviewer will definitely be listening for this nuance. Availability is the probability that your system is functional at any random point in time. It's often expressed as those famous nines. Reliability, on the other hand, is the probability that the system will work without failing for a specific period under certain conditions. So think of it this way. A system could be highly available because it recovers in milliseconds, but it could be incredibly unreliable if it crashes every hour. This distinction matters because it dictates your recovery strategy. If you focus solely on availability, you might ignore the root causes of crashes and just build faster reboot scripts. The failure mode here is flapping, where a service oscillates between up and down. To a user, that's just as bad as being totally dead. In an interview, you want to show you're thinking about the quality of the uptime, not just a raw percentage. You need to account for both the frequency of failures and the speed of the fix. Let's talk about availability, which is basically the metric of uptime. We usually measure this in nines. For example, 99.9% or 3 nines means your system can be down for about 9 hours a year. If you push that to 5 nines, you're looking at only 5 minutes of downtime per year. This works by measuring the total time a system is responding to requests versus the total time it should be working. It's a high-level view that matters because it's usually what you're legally committed to in a service-level agreement. However, a major failure mode here is measuring shallow availability. If your load balancer returns a 200 OK, but the database behind it is dead, your monitoring might say you're up while your users are seeing nothing but errors. In an interview, you should mention that availability isn't just about the network being reachable. It's about the system actually providing value. If you don't define uptime correctly, your metrics become a vanity project that masks a broken user experience. You need to look at success rates, not just heartbeats. Reliability is all about consistency. While availability asks, are you up right now? Reliability asks, can I trust you to finish this job? It works by looking at the probability of a system performing its function over a specific interval. If you're running a long-running data processing job that takes 12 hours, you need the system to be reliable for that entire window. Why? What matters here is that a system can have great availability but terrible reliability. Imagine a server that crashes every 5 minutes but reboots in 1 second. Technically, it's up 99% of the time, but it can't finish any task that takes longer than 5 minutes. That's a massive failure mode for mission-critical software. In your interview, highlight that for certain workloads, a system that stays up for a solid week is much better than one that's technically available but constantly stuttering. It's about matching your reliability targets to the actual needs of the work being done. You're building for consistency and long-term stability, ensuring the process completes without interruption. Mean time between failures, or MTBF, is our primary metric for how reliable a system really is. It works by taking the total operating time and dividing it by the number of failures. If your server runs for 1000 hours and fails twice, your MTBF is 500 hours. What matters here is that it gives you a predictable window of success, which helps with capacity planning and preventive maintenance. If you know a component usually fails after a year, you can replace it at month 11. A common failure mode, though, is misapplying MTBF to things that aren't repairable, like a light bulb or a specific type of hard drive, where mean time to failure is more accurate. Also, MTBF assumes a constant failure rate, but real systems often follow a bathtub curve where they fail early or very late. In an interview, using MTBF correctly shows you're thinking about the long-term life cycle of your infrastructure, not just the next 5 minutes. It's about building a sustainable, predictable environment for your software to live in by prioritizing component longevity. While MTBF is about how often things break, mean time to repair or MTTR is about how fast you can get them back up. It covers the whole cycle, detection, diagnosis, and the actual fix. What matters here is that lowering MTTR is often the most cost-effective way to hit your availability targets. You might not be able to prevent every hardware glitch, but if you can automate the recovery to happen in seconds, your availability stays incredibly high. The big failure mode here is speed over quality. If your automated fix just clears a cache without investigating why it filled up, the system will just crash again in 10 minutes. You're essentially lowering MTTR while also trashing your MTBF. In an interview, emphasize that a mature MTTR strategy includes robust monitoring and automated rollbacks, but also leaves a trail for post-mortem analysis. You want to show that you're patching holes and, more specifically, actually learning from every incident to make the system more resilient. It's about making the restoration process as invisible to the user as possible. One of the most direct ways to boost availability is through redundancy, which means having backup components ready to take over. You likely heard of active-active or active-passive setups. In an active-active configuration, all your nodes are handling traffic, so if one dies, the others just pick up the slack. In active-passive, you have a standby waiting in the wings. What matters here is that it removes single points of failure from your architecture. If your only database goes down, your availability drops to zero immediately. But redundancy isn't a silver bullet. A common failure mode is correlated failure. This happens when a bad configuration change or a specific bug hits all your redundant nodes at the exact same time. Now, instead of one node failing, your entire fleet is toast. When you're explaining this in an interview, show that you're thinking about diversity in your redundancy, like spreading nodes across different power grades or cloud regions. It's about ensuring that whatever kills the primary node doesn't also have the reach to take out the backup. Failover is the automated process that kicks in when a failure is detected, switching your traffic from a broken component to a healthy one. It works through health checks, basically heartbeats that say I'm still alive. If the heartbeat stops, the load balancer or orchestrator reroutes traffic immediately. What matters here is that it slashes your MTTR. If a human has to wake up at 3 a.m. to flip a switch, your availability is going to tank. Automation keeps the system running while you're still sleeping. But there's a dangerous failure mode called split brain. This happens when two parts of a cluster both think they are the primary because the network between them died, not the nodes themselves. They start writing conflicting data and you've got a massive mess to clean up. In an interview, don't just say you'll use failover. Talk about how you'll handle consensus and avoid split brain using tools like Zookeeper or etcd. It shows you understand the complex risks of the automation you're proposing. Reliability engineering is the proactive side of the house. Instead of just trying to recover faster, we work on making sure the system doesn't break in the first place. This works through deep root cause analysis, rigorous unit and integration testing, and component hardening. You're basically building a system that can withstand the expected chaos of the real world. Why? What matters here is simple. A highly reliable system is much cheaper to operate in the long run because you aren't constantly fighting fires or paying engineers for on-call emergencies. However, a major failure mode here is diminishing returns. You can spend months hardening a piece of code against a hardware failure that only happens once every decade. In a system design interview, you want to show that you're prioritizing your hardening efforts on the most likely or most damaging failure points. It's about being smart with your engineering hours. You're looking for high-impact improvements that prevent the most common crashes rather than chasing every possible edge case that might never actually happen. In the real world, failures aren't always all or nothing. We distinguish between total failures, where the whole site is down, and partial failures, where maybe only the search feature is broken. This works by decoupling your services so they don't have a hard dependency on each other. What matters here for your design is that it allows for graceful degradation. Users can still browse and add items to a cart even if the recommendation engine is offline. The failure mode to watch out for here is a cascading failure. That's when one small service fails and the resulting error messages or retries overwhelm another service, eventually bringing down the entire system. In an interview, this is where you talk about circuit breakers and rate limiting. You want to demonstrate that you've designed a system that's available enough by keeping the core features running while isolating the buggy parts. It's a sophisticated way to maintain high perceived availability even when individual components slip. It shows you're thinking about the user's journey. When you're designing for high availability, you'll eventually hit a wall where the cost of adding another 9 becomes astronomical. This is a favorite topic for interviewers because it tests your business sense. Moving from 3 nines to 4 nines means your allowed downtime drops from nearly 9 hours a year to less than an hour. To achieve that, you're usually moving from basic redundancy to global multi-legion deployments with automated failover and sophisticated health checks. What matters here is that you have to justify that 10x increase in infrastructure cost. If you're building a cat photo sharing app, the cost of that extra 9 might be way higher than the revenue loss during a brief outage. A common failure mode for junior architects is over-engineering for 99.999% uptime when the business only needs 99.9%. You've got to be able to explain the ROI. In the interview, point out that every additional 9 requires more complex coordination, which can introduce new failure points like configuration drifts or synchronization issues between regions. Let's look at a domain where reliability is the absolute king: banking and financial services. In these systems, data integrity is everything. You cannot have a transaction partially complete or a database record get corrupted during a crash. How this works in practice is through heavy emphasis on asset compliance and rigorous testing of every state transaction. It matters more that the system is correct than it is up during a massive hardware failure. If there's a risk of data corruption, it's often better for the system to stop entirely, essentially sacrificing availability to preserve the reliability of the data itself. A failure mode here would be a ghost transaction, where a user's balance is updated but the logs didn't clear, leading to financial loss. When you're discussing this in an interview, emphasize that you're prioritizing consistency and correctness over immediate response times. You're signaling that you understand the stakes of the specific industry you're designing for. It's about choosing the right tool for the job rather than just chasing the highest uptime number. Social media platforms often take the opposite approach of banks, prioritizing availability over perfect reliability or consistency. If you post a comment and it doesn't show up for your friends for a few seconds, it's not a disaster. This works through eventual consistency models, where the system stays available for writes even if the data hasn't propagated everywhere yet. What matters here is that users would much rather have a site that's mostly working than an error screen. If a social app went down every time a database node lagged, nobody would use it. The failure mode here is user confusion. If someone sees their post disappear and then reappear, it feels buggy and untrustworthy. When you're explaining this in an interview, talk about the trade-offs in the CAP theorem. You're consciously choosing availability and partition tolerance over immediate consistency because the cost of an outage is higher than the cost of a minor data lag. It's a pragmatic design choice that keeps the user engaged even when the underlying infrastructure is having a bad day. Finally, let's look at how these requirements change across different industries. A cloud provider might promise 99.99% for its core storage service because thousands of other businesses rely on it. In healthcare or emergency services, the reliability requirements are even more intense because a system failure could have life or death consequences. This table shows that there's no single correct number for availability or reliability. It's always a business decision driven by the cost of failure. Why? What matters here for you as an architect is that it helps you set realistic goals. A failure mode here is trying to apply a one-size-fits-all approach. If you build a simple internal tool with the same redundancy as a global payment processor, you're wasting massive amounts of time and money. In an interview, use these industry standards to anchor your answers. If you're asked how much uptime a system needs, start by asking what the business impact of an hour of downtime looks like. It shows you're an engineer, and more specifically, a strategic thinker who understands that every architectural choice has a price tag attached. So, we've broken down the fundamental tug-of-war between availability and reliability. In a system design interview, you've got to be razor sharp here. Availability is your uptime percentage, while reliability is the consistency of that operation over time. We saw how the math ties them together through MTBF and MTTR. You know, a common trap is thinking they're the same, but a system that crashes every 10 minutes can still be highly available if you're fast enough at rebooting it. That's why understanding the MTBF divided by MTBF plus MTTR equation is so vital for your toolkit. It lets you explain exactly why you're choosing redundancy to mask failures or hardening components to prevent them entirely. Being able to articulate that trade-off shows you're looking past the dashboard and actually managing the life cycle of the system, right? So that brings us to the end of our look at availability versus reliability. In a high-stakes interview, the real signal is how you justify your design choices. Try to explain how you'd handle a partial failure or why you'd prioritize availability over consistency for a social feed. Showing that you understand the infrastructure costs and the risk of over-engineering proves you can think like a senior architect. Subscribe to the channel for more topics. In the next episode, we will discuss CAP theorem, practical application, where we'll discuss core understanding, consistency, availability. Good luck with your prep.